On this fifth lecture, we will discuss some operating system structures and generic features that operating systems usually have. If we at this point take a look at what was presented in the very first lecture, or well, the kickoff lecture of this course, what is the high-level course outline that we will more or less follow? So far, lectures 1 to 4 have dealt with this first topic, computer organization and computer architecture. So basically, we have been asking what is the organization of a computer, how do the components fit in the software hierarchy, how does the processor actually execute programs. This is more or less the topic that the first assignment deals with. So what you are in practice doing is looking at these topics hands-on using the Hack virtual computer. Now, for the remainder of the course, we have to move on to the next topics. So next, we're going to be looking at operating system concepts and operating system construction. And then at the end of the course, of the last one or two lectures, we will talk about the operating system services from a programmer's perspective and take a look at the server-side considerations of all of these. But for now, for the following few lectures, we are going to be concentrating on these operating system concepts. These operating system construction ideas and concepts follow logically in this path that we have started from starting with hardware and then ending with this software abstractions. So all the way from hardware to very high level applications and high level application programming. Let's begin with a very brief recap of the computer system architecture and this from hardware to software thinking that we are following on this course. So all modern computing devices, all modern computers follow what is the generic blueprint for a computer, for a information processing device called the von Neumann architecture. And of course, the idea with the von Neumann architecture is that we have the computer in the middle between input and output devices, and the computer itself consists of some processor and a separate memory unit. And the idea of the von Neumann architecture is to implement what is called the programmable computer, meaning that whatever software is loaded in the memory determines what the computer is actually doing. So the same hardware can be used to solve different problems using software. Of course, the von Neumann architecture is only an idea. It's an abstract idea of how computers generally work. In practice, if we look at things in perspective, there are more layers to the architecture from both the software and the hardware perspective. So if we start from the bottom, there exists actual hardware devices such as devices for input-output networking, memory modules, etc. Then there is a more or less a hazy layer of middleware. Sometimes you might call this firmware, where certain modules here are hardware modules and some other modules might be in fact software modules. So the line between hardware and software here is in a way blurred. Usually we can, however, agree that the software hierarchy begins where all of the hardware considerations end, and pretty much the first step above these hardware considerations is the operating system for a computer, and all the other software components then are situated on top of the operating system. The difficulty of talking about how computing systems work is because everything is so very complex. So as an example, here the software stack of the Android mobile operating system. So there are a few dozens of different software components, all of these, which more or less is related to the Android operating system and the applications that run on top of it. So there are various different levels of software abstraction on top of the abstraction that all of the hardware provides. This complexity is one of those realities that we just have to accept. Computing devices are inherently complex. What we can take away from this, however, is that on these lower levels, say around here, or well below the very high level and more or less low level software abstractions, there are more or less different services that need to be offered to the high-level applications. So in the case of this mobile operating system, there are, for example, there is, for example, a camera service, Bluetooth, GPS, Wi-Fi, radio, and so on. All of these are services that the Android operating system provides for the applications that are running on top of it. This brings us neatly to the question of how is an operating system actually constructed so that it is able to provide all of these services. Operating systems usually are pretty big. They are something along the magnitude of millions or tens or hundreds of millions of lines of code. And all of that complexity needs to be managed somehow. So how is an operating system actually constructed? How would anything in this Android operating system make sense? In the most generic terms, an operating system is a collection of software that manages data or information exchange between different software components and hardware drivers. And we use what is called firmware to communicate between software and hardware. Another important feature that at least modern operating systems have is the ability to enable the parallel execution of different programs, resource monitoring, and performance monitoring. So three inherently complex tasks that operating systems tend to do at least reasonably well. Usually this is done by providing a set of services to the application programs. Namely, the operating system provides something called a process abstraction. It also provides some sort of file system abstraction and also processing time abstraction or virtual processor abstraction. We will come back to these ideas of providing abstractions in a few minutes. Before we get to that though, let's consider a brief moment of history. That is, how did we get to where we are now? How did operating systems become what they are today? So what we started out with about 40-50 years ago was that we had computers which were inherently used by very privileged specialized people, and there weren't very many of them. That is there weren't that many people who knew how to operate computers, and there weren't that many computers either. And that was basically because computers were very expensive, much more expensive than people. So we could actually hire many computer technicians to run one single computer. In that context, it basically meant that computers were more expensive than people, so it was reasonable to optimize the operation of the hardware. And also, there wasn't really a need for any multitasking because computers were so expensive compared to people that people could afford to wait for the computer to finish whatever job it is doing at the moment. And basically, that is why early computers did not have any notion of multitasking. That, of course, meant that early operating systems were very different from what they are now. So these factors affected how we designed computing systems. The first computer systems, we had multiple users who would use what was called a dumb terminal to connect to a computer, and people would do this one at a time. So at that point, there wasn't really a need for any complex operating system. All we needed was basically a system library which provided many useful subroutines or functions, functionality that helped to abstract some of the hardware features away from sight of these computer technicians. Funnily enough, this is actually very similar to what we are doing in the first, or what we were doing in the first assignment with the hack computer. So we were considering a very rudimentary computer where the operating system is just a collection of software libraries, and we do not have to consider a lot about, for example, how to run multiple programs consequently, at the same time. These old operating systems were what we would call batch systems. So these would run programs one at a time. A user would load a program, usually using a cassette tape or a punch card or a cartridge, some sort of transferable media. And basically, the computer would load this program from the media, run the program, print results, and then the user would move on to do what it is they do for a living, and then the next user would come and load their program, and so on and so on. What is important to realize at this point about the use of these systems is that batch systems had no security mechanisms as such. So if a program had some programming flaw in it, it would crash the entire computer. Additionally, in batch systems, input-output computation were equal operations. So programs could access memory directly. Actually, programs could access all hardware resources directly. Again, this is very analogous to the first assignment when programming with the hack computer. As time passed, we gained more and more processing power, and it was no longer efficient for computer programs to manage everything on their own. So pieces of firmware, software that controls hardware, came along. So now the operating system would make a request for some input-output operation, then the piece of software, the operating system as it was then, changed some process to one that handles input-output and continued the actual computation task once the input-output operation was completed. This meant that now some piece of software, what is now the operating system, needed some mechanism of how to interrupt programs. And that means that the programs and the operating system must have some way of telling the processor to stop what it is doing right now and move on to some other task. And that is what is known as an interrupt signal. Interrupt signals are basically the building block for responsive computing systems, which can run many programs at the same time. Basically, the idea here is that we have some piece of software, the operating system, which can control the execution of all other programs on the CPU. And when this interrupt signal happens, the processor stops executing some application program's code and switches back to the operating system's code. Later on in the course, we will talk more about how to manage multiple programs and their execution at the same time. For now, let's continue with our history lesson. So at some point, computers became more and more common. So it made sense to be able to transfer programs from one computer to another. This is basically the concept of relocatable program code. So the idea is if you have made a program for one computer, if you want to distribute it, it should work on some other computer as well. And nowadays, this is more of a, this is pretty much as an obvious thing, or this is how all computers work, but about 40 years ago, there were many computer manufacturers, all of whose hardware differed a little bit from each other. So a program that worked on one computer did not necessarily even compile on another. Another thing that the popularity of computers caused was this idea of multiprocessing. So the idea of having multiple programs in the memory simultaneously while being executed at the same time, also simultaneously or in parallel. On some very specialized systems, you could also have multiple users running these programs at the same time. There also has to be some consideration as to what is the size of the program or how much computing power is one program taking. Should small programs yield while bigger programs are hoarding all of the computational resources? These ideas of relocatable program code and also memory management also brought us the idea of distinguishing input-output operations from actual processing on the CPU. These ideas on their own are pretty great, but it does come with complexity. Namely, this multiprocessing and memory management and relocating program code means we need memory management. Or rather, we need to control how individual programs access the hardware resources, because one program is not allowed to crash another or the whole computer. So the complexity in this is that now whatever operating system we have has to keep track of all the programs that are being run at the same time, in addition to keeping track of all possible interaction between programs. Sometimes programs need to exchange some data. So also there needs to be some sort of way to share the data if programs want to communicate with each other. Okay, so if we move on to more modern times, at some point in the timeline, computers became, or computing power processors became really inexpensive. CPUs became more powerful, meaning we could have several users use one powerful mainframe computer, via those dumb terminals. We could divide processing time between users. We could have more users, and that of course meant more users sharing the same computing resources, the slower the entire computing system became. And of course now in 2020, basically anyone can afford a microcomputer. So computers are ultimately so cheap that everybody can afford at least one. Probably we have multiple processors on us at all times. So you probably have a PC somewhere, you probably have a smartphone, you may have a number of computing devices. This more or less meant some changes to the multi-user batch systems. So operating systems had to adapt to the fact that now users did not anymore have to compete for computing resources. So in the beginning we had a one user, one PC ratio, and later on we had more like a one user and multiple PCs, multiple processors. This of course came with its own problems. So now we have many things such as memory management, user management, process management, more civilized multiprocessing features, and so on and so on. And the fact that we have also networking, so every single computing device, is connected to the internet, means it's possible to share resources, unlike in the previous decades. With all of this complexity in mind, how does an operating system actually achieve any of these? Well, the first concept we have to look at is called processes, or a process. So basically the first and most important task of an operating system is to coordinate the control and execution of all other programs, specifically the machine code, each instruction of every single program that is in the memory. In real life, this is a very difficult task because we have many different contexts of use, several different programs that we want to run at the same time. We also have several hardware devices. We usually have at least one processor, at least some memory, one or more hard drives, and other peripherals. So all of this coordination in real life is not very easy. And the way that modern operating systems do this is basically with a tactic called divide and conquer. So what we do, or what they do, is they split these difficult, complex problems into smaller subproblems and just deal with all of the complexity one problem at a time. One way of managing the execution of all possible programs on a computer system is through the abstraction called a process. So usually operating systems provide an abstraction called a process. And what a process is basically everything that is needed to run and execute one single program. So it's all of the code for that program that ultimately ends up being executed by the CPU, and everything else surrounding the code. The formal definition for this is that a process is the sequential execution of instructions in its own memory space. What is important to remember here is that a process has two sides to it. There is first of all the sequential execution of program code, and also the state of the process. What I mean by sequential execution is that processes themselves do not provide any way of executing programs in parallel. So all execution in a computer system is more or less sequential. So we consider one instruction each after another. Now, here it's important to remember that this is more or less, again, the idea of how processors, how computers work. In practice, you might have a computer that has multiple processors, but more or less this idea of everything being sequential and we consider all execution sequential is just for simplicity's sake, but in practice you might have computing systems with multiple processors. That is just something to keep in mind. On the other hand, everything that works with just one processor or everything being sequential also scales up. So it is possible to transfer every single idea from this simplified view to a multiprocessor environment. Anyway, moving on. So the state of the process. So by the state of the process, what I mean is all of the memory that one process, one program needs to manipulate in order to be processed. So every single memory location, every single value, every single register use, every single bit in a file system, just everything that the computer program needs or will eventually touch. Another thing to remember is that a process is not the same as a program. And this is a very important distinction for a couple of reasons. For now, just remember process is not the same as a program. We differentiate between processes and programs for a couple of reasons, but let's just head to the to what it means in practice. So a computer program in its most basic form is a collection of program code. And a program could be any program that you have stored in the computer. So for example, it could be a web browser, could be a word processor, it could be a command line utility, whatever it may be. Any collection of program code, any executable is a program. When compared to a process, a program is just one portion of it. So a program is a part of the state of the process. So let's give an example of what this means. So let's say we have a computer system that has two users. Both users have access to the same programs. If user number one executes some program and then user number two comes along some time later and executes the same program, they're using the same program, but of course these users' actions usually do not affect each other. So therefore you would say that these users are running the same program, but they are running two different processes. Well, at least this is how it would work in a sane multi-user modern operating system. Another consideration here of why programs and processes are different, a program can also be above a process if you put it in terms of hierarchy, so which controls which. So one program can start new processes. So program code can in fact ask the operating system to start other programs. This is how we start programs in the first place. So in your operating system, there probably is some interface, for example, in Windows, the start menu to start new programs. Well, the start menu itself is a program, and that program needs to be able to start other programs. If we try to visualize what is the difference between a program and a process, it might look a bit like this. So in the bottom part here, we have the hard disk full of all sorts of computer code, so either data or program code. And if we pick any computer program that is stored there on the disk, in order for us to execute it, we have to load the program code into the RAM memory, because that's where the CPU is able to efficiently access it. So when running some program, it starts from loading program code to the RAM memory. Loading a program is what creates a process. So once we load the individual program code, that is all well and good, but it's not enough to actually execute the program. That is because the program will actually need some space in the memory for any computation that happens while the program is being executed. So let's say we had some variables, some calculation, and then we wanted to store the results of those calculations. Well, in order for that to happen, we need to reserve some space in the RAM memory. And we also need to reserve other areas of memory for any data items that the program manipulates. And that is all parts of the process's memory space. So in particular, in the memory space, there is space for the code itself, static data items such as variables and numeric values that are declared in the program code. And then there are a couple of memory sections called heap and stack. The heap and stack are basically memory areas reserved to store some intermediate results from any calculations or function calls or any of that sort. They are basically the sandbox that the program gets to play with, reserved for it in the RAM memory. This space in the RAM memory is also called the address space of this process. And once this address space has been reserved, only then can code execution begin. So what I'm trying to say here is that the program code itself is only a very small part of what is required for some program to be executed on the CPU. And therefore, the ideas of a program and a process are different, similar, but yet two different actual concepts. Now that we have looked at what processes and programs mean in practice, let's take a couple of formal definitions. These definitions are useful for the purposes of understanding how the processes actually work. So if we start with single processing, that is the idea of one process being executed at one time. That means that if you have a computer or operating system which is only capable of single processing, it will not be able to run multiple programs at the same time. Older operating systems, batch operating systems, for example, MS-DOS or the original Macintosh systems were single processing systems. Single processing systems are nowadays outdated and old. The idea here is that the user of a PC computer is doing one single task at a time, therefore there is no need for multiprocessing. Nowadays, this probably is not very practical approach for building an operating system. Multiprocessing, on the other hand, is what all modern operating systems do. The idea is that you can have multiple programs, multiple processes running at the same time. The first multiprocessing operating systems were Unix, OS/2, Windows 95, and all of the Windows operating systems from Windows 95 onwards. One more important concept relating to processes is a thread. So sometimes you don't hear, especially application developers, speaking about multiple processes, but they speak of multiple threads instead. A thread is a close concept to a process, because a thread is basically the idea of having some sequential execution of instructions within a process. So basically a process within a process is what we call a thread. This allows for the parallel execution of instructions within one process or one program. They are sort of lighter mini processes within a process, and the difference between a process and a thread is that a thread has no access to the hardware resources that the operating system provides. Instead, they share resources allocated to their parent process. The last definition of a term, memory space, basically means all the space which the execution of a program needs. Literally, it means all the parts of the main memory to which the program has access to. Each process has its own memory space, so to one process, it actually appears as if you had your own CPU and your own RAM memory. So this is what is in practice called sandboxing, or isolation of program execution, and it's done for safety purposes. So remember previously I said that one process or one program is not allowed to interfere with the execution of other programs or other processes. Well, this in practice is the safety mechanism of how you do it. You isolate each process into their own memory space. Why these definitions are important? Well, usually when we talk about what the operating system does, we often end up talking about processes. And when we talk about processes, when we talk about parallelism, that is executing programs at the same time, or multiprocessing, what we are actually talking about are processes, threads, and their synchronization, how to make different processes be executed at the same time, and how to synchronize that parallel execution. At the same time, if we talk about sandboxing and isolation of execution, what we mean specifically is the memory space of different processes. So please keep in mind that in future, when we talk about these concepts, this is what we actually mean by these terms. Now that we have covered some basic terminology, let's briefly discuss some of the main features for an operating system. So what is it that the operating system needs to do in practice? The main tasks of what an operating system needs to do can be represented with three main concepts, or three main features or tasks. These are that the operating system needs to provide a platform for virtualization. That is the virtualization of hardware resources and providing a virtualized software platform that hides all of these hardware specifications. The operating system also needs to provide concurrency for the different processes that are being executed at the same time. And finally, the operating system needs to provide the persistence for all of the software that is running on it. That is, in practice, the operating system needs to provide some sort of file system for all of those programs to store data persistently. We will discuss each of these ideas on the upcoming lectures, but also note that these features are discussed extensively in the course book. So if you want to know more and why to take this approach, these three main features, and looking at an operating system through them, please read the course book, the Operating Systems 3 Easy Pieces book. If we quickly dive into each of these main tasks, starting with virtualization. What virtualizing hardware resources means from an operating system perspective, in its basic form, give each running process their own virtual processor and or own virtual memory. So to a process, it looks like there are no other programs using the processor and the memory space in the computer system. This way, processes play in their own sandbox very nicely and do not have to know anything about the other processes or what they are doing. The job of the operating system is then to divide physical or real resources among these virtual execution spaces. Then concurrency, in its basic form, means making programs work in parallel with shared resources, or making these multi-threaded programs or having multiple processes work in the first place, and making them work so that this parallelism is implemented well and efficiently. Often we see a couple of terms related to concurrency. Here they are concurrency and parallelism. So what concurrency is the feature that we want to discuss, and what that means, in other words, is multi-programming. We have multiple different processes running on one physical processor. What parallelism, on the other hand, means, we could have multiple concurrent processes being executed using multiple different physical processing units. So the difference between multi-programming and multi-processing is key here. So we do not consider that we have multiple different physical processors, while again that could be the reality that your computer has multiple processors. But again, these ideas of multi-programming or concurrency do scale up. So oftentimes we do not have access to as many physical processors as we would have processes running on a computer, and that's why talking about concurrency makes sense. Finally, the concept of persistence. So the operating system implements some sort of saving and retrieving of data for the application programs, so that data can be more or less permanently be stored. In practice, what we have to implement within an operating system is a disk management system and a file management system. And then we need to provide some mechanisms for moving files between system memory, RAM, and disk or hard drive. We will discuss each and every one of those main tasks and how they might be implemented in later lectures. For now, what do you need to remember from this lecture? So we covered basically three main topics today. First of all, the definition of what an operating system is, or at least what it does in terms of those main tasks. We also covered some terminology for processes, threads, and that sort of things. So keep in mind the difference between a program and a process. Finally, those generic features of what an operating system needs to provide, that is virtualization, concurrency, and persistence. And if these features are basically what an operating system needs to do well and efficiently. If it achieves those, then, well, the rest is all trivial.